Welcome to Understand the Math. In this Calculus 1 video, we're exploring one of the most important concepts in calculus, the limit of a function. You'll learn the intuitive idea of a limit, see how one-sided limits work, and then move on to the more formal definition of a limit. We'll also look at infinite limits and vertical asymptotes. Along the way, I'll guide you through clear examples so you can see how limits really work in practice. Be sure to download the free guided notes to help you follow along step by step. Let's start by learning about the intuitive definition of a limit and walk through some example problems. Limits are needed to find the tangent line to a curve or the velocity of an object. We went over both of these concepts in a previous video. Suppose we have a function f of x that is defined when x is near the number a. We can use a limit to describe the value of our function f of x when x is near a point a. The limit tells us the value of a function as we get close to a point but not necessarily reach that point. As x gets close to a up here in our graph, our function is going to go from the right and from the left to this value L. It does not matter what is happening at x is equal to a, it only matters what is happening near x is equal to a. Mathematically, we can write this as the limit of f of x as x approaches a is equal to L. Let's now look at some examples. We want to find the limit of f of x as x approaches a and then compare it to f of a. Let's look at our first example. We want to find the limit as x approaches a of f of x. And to do that, we're going to see what our function value equals when we get close to a. So if we go from the right and from the left, we can see that our function value is going to equal L. So we say that our limit is equal to L. Now let's look at what f of a is. Because we have a closed circle right here, we can say that f of a is equal to L. So in our first example, the function value at a and the limit at a are the same thing. Let's now look at our second example. We're going to look at the limit as x goes to a of f of x. Let's go back up here to the graph and see what happens as we approach a from the right and from the left. Our function value is going to get closer and closer to L, so that's what our limit is equal to. Now let's look at f of a. Notice at a that our function is defined right here. That value is different than the value L. So that tells us that f of a is not equal to L. Let's look at our third example. The limit as x approaches a of f of x is going to equal L. This is the same thing we had in example 2. As we approach from the right and from the left, our function equals L. Now let's look at f of a. F of a is actually undefined because we have an open circle at a. So we say f of a is undefined. And this is not equal to L. Let's summarize this before going on. In example 1, our function value at a was equal to our limit. In example 2, our function value was defined but not equal to our limit. And in example 3, our function value was undefined and also not equal to our limit. Now that we have an intuitive understanding of what a limit is, let's learn about one-sided limits and look at some examples. we're going to start with a left-hand limit. When we have a left-hand limit, we start with a point to the left of A, and we call this point A from the left. This graph is really enlarged so that you can see A from the left and A, but in reality, these points are really, really close together. A left-hand limit is defined as the limit as x approaches A from the left. Let's look down in our graph. That means we're traveling along and we're approaching A from the left of f of x is equal to the value L. Let's now look at a right-hand limit. When we have a right-hand limit, we start with a point to the right of A. We call this point A from the right, and this point gets close to A. Our right-hand limit is defined as the limit as x approaches A from the right of f of x. So let's look over here on our graph. We're going to come along here and we're going to approach A, and the value of f of x is going to approach L. So our limit is equal to L. Let's now look at some examples where we're going to find the indicated limit. For both of these limits, we have to refer to the graph here on the right. In our first example, we're going to be looking at the limit as x approaches 2 from the left. So as we approach 2 from the left, our function is going to approach the value 2. So we say that this limit is equal to 2. Now let's look at our second example. For this one, x is going to approach 2 from the right, so we're going to come this way on our function, and you can see that the value is getting closer and closer to 3. So we say that our limit is equal to 3. Notice that our limit from the left doesn't equal our limit from the right. This is going to be really important in our next definition. This leads us to what we call the general definition of a limit. The general definition of a limit tells us that the limit of f of x as x approaches A is equal to L if and only if the limit of f of x as x approaches A from the left is equal to L, and the limit of f of x as x approaches A from the right is also equal to L. This just means that the limit exists if the left-hand limit equals the right-hand limit. It doesn't matter what happens at x is equal to A. Let's walk through some examples so that we can really understand this. In our first example, we're asked to find the limit of f of x as x approaches 2, and we're given that f of x is a piecewise function, and it's defined as 2x when x is not equal to 2 and 6 when x is equal to 2. When you're evaluating a limit of a piecewise function, it's best to start by graphing the function. I have a video on graphing piecewise functions if you need to review that. Let's graph our function. When x is 2, f of x is equal to 6, so let's put a solid dot right here. And then when x is not equal to 2, f of x is 2x, which is just a straight line through the origin with a slope of 2. To graph this line, I'll put a point here at the origin, and then when x is 2, f of x is going to be 4, so we'll put a point here, and then we'll just draw a line that connects those 2 points. I'm now going to draw an open circle right here to indicate that our function is not defined at that point, because it's equal to 6 when x is equal to 2. Now we can start talking about our limit. We want to evaluate our limit as x approaches 2. So let's look back at our line and see what the function goes to as we approach from the left and we approach from the right. Can you see that our function value is going to approach 4? Because of that, we can say that the limit as x goes to 2 of f of x is equal to 4. The limit from the left was equal to the limit from the right. Let's now look at our second example. This is really a classic calculus example to do when we're looking at limits. We're going to evaluate the limit as x goes to 0 of x divided by absolute value of x. The absolute value of x is a piecewise function, so let's go ahead and start by writing down what it is. The absolute value of x is defined to be x when x is greater than or equal to 0, or minus x when x is less than 0. If you haven't seen that before, you might need to commit that to memory. Now we can evaluate our limit. We're going to look at our left-hand limit and our right-hand limit and then see if those two pieces match up. We're going to look at the limit as x approaches 0 from the left of f of x. When x approaches 0 from the left, our absolute value function is equal to minus x. So we can write this as the limit x goes to 0 from the left of x divided by minus x. The x's cancel, so we have the limit as x goes to 0 from the left of negative 1, and that's just equal to negative 1. Now let's look at our right-hand limit. The limit as x approaches 0 from the right of f of x is equal to the limit as x approaches 0 to the right of x divided by our absolute value function when x is positive. So that's just x. So we'll put an x here. So this is the limit. X goes to 0 from the right of 1, which is 1. Now we have to see if our left-hand limit equals our right-hand limit. Our left-hand limit is negative 1, and our right-hand limit is equal to 1, and they're not equal. I put a graph up here on the right just so that we could see this graphically before we come to our conclusion of what the limit's going to equal. When x is greater than or equal to 0, our function is equal to 1, and we're going to put a closed circle there. And then when x is negative, our function is equal to negative 1. And we're going to put an open circle here because the absolute value of x is only equal to minus x when x is less than 0. Looking at this graph, you can see that our limit from the left does not equal our limit from the right. So we can say that the limit as x goes to 0 of x divided by absolute x does not exist. And we abbreviate that by DNE. In example 3, we're given a function f whose graph is given, and we're going to evaluate the following limits. Let me move this up a little bit so that we can see the limits. The first limit that we're going to evaluate is the limit as x goes to minus 2 from the left of f of x. If we look at our graph and find the point minus 2, we have to look at what happens to the function as we're to the left of minus 2 and going towards minus 2. You can see that our function is going to equal negative 1. So we say that our limit is equal to minus 1. Now let's look at part B. For this one, we are also going to take the limit as x goes to minus 2, but we're going to go from the right of minus 2. If we look up at our graph, we're going to go along the function as we approach minus 2 from the right, and you can see that our function value is going to approach 1. So our limit is equal to 1. Now in part C, we're asked to find the limit just as x goes to minus 2, not from the right or from the left. To find out what this equals, we need to see if the limit from the left is equal to the limit from the right, and we can see that the limit from the left is not equal to the limit from the right, so we say that this limit does not exist, and we write it as DNE. Now let's look at part D. For this one, we're going to take the limit as x goes to positive 2 from the left. Let's focus on 2 on our graph, and we're going to come from the left, and we can see that the value is going to equal 1. Now for part E, we're going to go back up to our graph, but this time we're going to approach 2 from the right, and we can see that our function is going to equal 2. So let's write that this is equal to 2. For part F, we want to see what the limit as x approaches 2 is equal to. Notice that the left-hand limit and the right-hand limit are not equal, so we say that this limit does not exist. Hopefully you're getting the hang of this. Now let's look at our third set of examples. This is going to be different than the first two that we just looked at. We're first going to look at the limit as x approaches 4, so let's put our eyes here on 4. We're going to look at what happens as we approach 4 from the left. So we're going to go this way, and you can see that our function is going to approach the value 2. So this is equal to 2. Now let's see what happens as we approach from the right. As we approach from the right, our graph has what we call oscillatory behavior, and it oscillates between two values and never settles down. When that happens, we say that our limit does not exist. So let's write D in E, because it's not equal to one value. It just keeps bouncing around between values. Now let's look at I. This is the limit as x approaches 4. So again, we're going to look at the left-hand limit and the right-hand limit, and we're going to notice that they are not the same. So we say that this limit does not exist. Let's now look at our fourth example. When I've taught this example in the past, this is the one that students find most challenging. In this example, we're asked to sketch the graph of f of x, and then we're asked for what values of a does the limit of f of x as x approaches a exist. Let's not worry about that part for right now. Let's start by graphing f of x. Notice that f of x is a piecewise function and it has 3 pieces. When I look at this function, I think the middle piece is the easiest. So let's graph that part first. Our function is equal to x, which is just a straight line through the origin, and it goes from -1 to 1, and it's defined at -1, but not defined at 1. So our graph is going to look like this, and we're going to have a closed circle at -1 and an open circle at +1. Now let's graph this piece. That is a parabola. It opens upward, and it's centered at the point 1, 0. It's defined at x is equal to 1, so we'll put a closed circle here, and then go ahead and plot the parabola. When x is 2, our function is 1. When x is 3, we have 3 minus 1, which is 2. That becomes squared, and it's equal to 4. So we can go ahead and graph the parabola. Now let's look at this piece. I think that piece is the hardest to graph. It is a straight line, and it has a slope of -1. For our piecewise function, it starts when x is equal to -1. So let's go ahead and let's plug in -1 into our graph, and we get 2 minus a -1, which is equal to 3. So we can put an open circle right here. And then our function is a straight line with a slope of -1, so we can just draw the graph like that. Now we can go ahead and answer our limit question. We want to find out for what values of a does the limit exist. For this question, what we want to do is start by thinking about the opposite. Looking at our graph, we want to determine for what values of a does the limit not exist. Let's write that down. So we want to see where the limit does not exist. If we look at x is equal to -1, we can see that the left-hand limit does not equal the right-hand limit. So let's write down that our limit does not exist at x is equal to -1. Let's now look at what happens when x is equal to 1. Can you see that the limit from the right does not equal the limit from the left? So we can say that our limit does not exist at x is equal to +1. To find out then where the limit does exist, I think it helps to go ahead and just draw a quick graph. We'll label this as x, and then we'll put -1 and 1 on it, and we're going to put an x at those points. So our limit is going to exist in that interval, in the interval between these, and then in the interval to the right. So we can say that our limit exists for -infinity to -1. We're using interval notation, union -1 to 1, union 1 to infinity. So that's our answer. Sometimes limits can approach infinity or -infinity. These types of limits are called infinite limits. Let's learn more about these and also about asymptotes, since these two topics are related. Let's first talk about asymptotes. There are three main types of asymptotes. A horizontal asymptote, which is written as y is equal to some constant b. Slant asymptotes, where y is equal to mx plus b. And then vertical asymptotes that are defined by the equation x is equal to a. Infinite limits arise from both slant and vertical asymptotes, but for right now, we're just going to focus on vertical asymptotes. And we'll talk about slant asymptotes later in the course. Just like asymptotes, infinite limits can be categorized into three different types. Let's look at the first type. The function in this first graph has a limit that approaches infinity from the left and from the right. Since our function approaches infinity from the left-hand side and the right-hand side of a, we can say that the limit of f of x as x approaches a is equal to infinity. The function in the second graph also has an infinite limit, but this time, as x approaches a, the graph on the left and on the right approaches negative infinity. So we say that the limit of f of x as x approaches a is equal to -infinity. The function in this third graph is also an infinite limit, but it's different from the first two. Here, as x approaches a, from the left, we go to -infinity, and from the right, we go to positive infinity. Because the left-hand limit and the right-hand limit are not the same, we have to say for this situation that the limit of f of x as x approaches a does not exist. Before we look at some examples, I want to point out that when a limit equals infinity or -infinity, such as we found in example 1 and 2, these limits also do not exist, but we don't write them as D and E because it's more descriptive if we write them as infinity or -infinity. Let's now look at two examples so that we can learn how to evaluate infinite limits, because these can be really tricky. In our first example, we have a function f whose graph is given, and we're asked to evaluate the following limits. Let's move this up so we can see our limits. The first limit that we're going to evaluate is the limit as x approaches 2 of f of x. Let's go up here and highlight 2, and then let's look at our function. As x approaches 2 from the left, we go to -infinity, and as it approaches from the right, we also go to -infinity, so this is equal to -infinity. Let's look at part B. For this one, we're taking the limit as x goes to 5. Let's go up here then and look at 5. And our function from the left goes to infinity, and from the right, it also goes to infinity. So this is equal to infinity. Now let's look at C and D. For both of these limits, x is going to -3. So let's go up here and look at that on the graph. From the left, it's going to minus infinity. And from the right, it's going to plus infinity. Let's write that down. So the first one is coming from the left, and it's minus infinity. Second one is coming from the right, and it's plus infinity. Those two limits are different, so we can say for part E that the limit as x goes to -3 of f of x does not exist. So we write D, N, E. We have one more part, and this part asks us to find the equations of the vertical asymptotes. I always like to ask students this because I think it's just good practice. Notice that we have a vertical asymptote at -3, at 2, and at 5. And we can write the equations for these vertical asymptotes as x is equal to -3, x is equal to 2, and x is equal to 5. So just remember, any vertical asymptote can be written as x is equal to some number. Let's now look at our second example, and I think this is the hardest one of the entire section. In part A, we're asked to find the limit as x goes to 2 from the left of the function 4 divided by x minus 2. Whenever you evaluate a limit, the first thing you need to do is use direct substitution and just plug in what x is equal to. This is equal to 4 divided by 2 from the left minus 2. I think it's easiest to evaluate this if we draw a little number line, put a 2 on it, and then put a 2 from the left, and then say, okay, let's let this be equal to 1.99. I just think it's easier to have a concrete number in there. This then becomes 4 over 1.99 minus 2, which is 4 over minus 0.01. Now, that number is going to get a lot smaller as we approach 2 from the left. So it's going to be minus 0.000, lots of zeros, and then a 1. So what we have here is 4 divided by a really, really small number that's negative. So we can write this as 4 divided by 0 from the left. Up here in a box, I wrote down what this equals. If we have 1 and divide it by a really, really small number that's negative, it's going to equal minus infinity. So we can say that this limit is equal to minus infinity. Let's now look at part B. Again, we're going to start by plugging this in. So this is 4 divided by 2 from the right minus 2. We can think of a number 2 to the right as maybe 2.01. And then we subtract 2. So this is 4 divided by 0.01. So this is 4 divided by 0 from the right, just meaning it's really close to 0, but it's positive. And this is equal to positive infinity. I have that formula written up there if you want to memorize it. Now let's look at part C. We're going to begin by plugging in that x is equal to 0 from the right. So we have 0 from the right minus 1, all divided by 0 from the right quantity squared, 0 from the right plus 2. 0 minus 1 is just minus 1. And then 0 from the right squared is going to be positive, so we write that as 0 from the right. And then 0 from the right plus 2 is just 2. So we have minus 1 on top, and then a 0 that is positive times 2 gives us a 0 from the right. This is going to be equal to minus 1 times 1 over 0 from the right, which is minus 1 times infinity, which is equal to minus infinity. And that's it. To really master these concepts, make sure you work through plenty of practice problems on your own. That's really the only way to learn calculus.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.